Thank you for the introduction. Good afternoon, everyone. As mentioned earlier, this is very timely, and it's in particular nice to bring together theorists, experimentalists, and the different implementations. This is the outline of my talk. I will, so I'll start with the introduction to superconducting qubits. I was asked to put together a bit of a perspective on how superconducting devices are useful as QuDits. Hopefully this will help in particular, this will be helpful in particular for people working in other fields. The second main topic of the talk will be control of qutrits based on flux superconducting devices. I will talk about essentially some experimental details of what Sahel presented in a previous talk, and then I will discuss briefly our randomized benchmarking process characterization for a single qutrit. And in the final part of my talk, I will discuss a proposal for the implementation of an entangling gate between two qutrits based on parametric driving. All right, so I'll give first a brief introduction to superconducting qubits, which hopefully will help convey a bit better where superconducting qubits stand in terms of their properties and how these properties enable QDIT-based quantum computing. So any superconducting qubit contains a Josephson junction, a structure formed by two metals separated by a thin tunnel barrier, and electrons can tunnel across. So at the microscopic level, this is the tunneling Hamiltonian, which moves electrons from one side of this barrier to the other. Now, in a superconductor, electrons are bundled in Cooper pairs. And if you try to move an electron across, this costs some finite amount of energy, twice the superconducting gap. So if you want to move electrons, you can actually only do so in pairs. So this happens via virtual two-order process, which eventually results in a coherent tunneling process of single Cooper pairs. So when you look at this system, there is a low-energy Hamiltonian described by this simple expression here, where essentially N, L, and Nr are the number of Cooper pairs on the two sides of the barrier. So the dynamics is simply described by a process where these numbers change by -1 and +1. So that's a Cooper pair moving this way, or the reverse of Cooper pair moving the other way. So the scale for this is the Josephson energy. Another contribution to the energy next to this Josephson tunneling contribution arises from the charging, from the electrostatic energy in the system. So if you have an imbalance of Cooper pairs, this generates an electric field, and this leads to an energy contribution, which is simply the effective energy of a capacitor. So this scale is the charge of a Cooper pair divided by twice the capacitance, and depends on this charge imbalance between the two islands. Finally, if you make superconducting devices or you put several of these Josephson junctions in a loop, each of the tunneling terms that I introduced earlier, the terms that move a Cooper pair around, they come with a phase factor, where this phase factor here has an F, which is essentially the magnetic flux applied to that ring. So this is akin to an Aharonov-Bohm phase, or equivalently, if you work in condensed matter, Poisson substitution. And finally, if you build the circuits with multiple Josephson junctions, you usually also have voltage and current sources, and these come with their own terms. So essentially, in brief, these are the ingredients that you need to form superconducting qubits. Any superconducting qubit contains one or more of these Josephson junctions. And over time, so there's been now well over 2 decades of development in the field. There were several main classes of qubits that played an important role in the development of the field. In the early 2000s, phase qubits, which are formed by this single Josephson junction bias current source, played an important role. Over the past, well over a decade, the transmon qubit was the main system used in quantum computing, and this derived from an earlier version of qubit named the charge qubit, demonstrated in 1999. Another class of superconducting qubits that's also quite prominent are flux qubits. These are formed by superconducting loop with one or more Josephson junctions. You can see in this picture here a loop with 3 Josephson junctions. This is the first proposal of a flux qubit, and more recently, another type of flux qubit, the fluxonium, became very prominent on account of some very interesting properties. So now, just to comment a bit more about some of the properties of these devices and how they are relevant for qubits. I'm showing again here, so this is a diagram from a review paper by Irfan Siddiqui, which illustrates this very nicely. So this diagram shows 3 main types of superconducting qubits, the transmon, the fluxonium, and the flux qubit. And what you see in these lower panels here in black are representations of the potential energy in terms of the phase degree of freedom. So this phase degree of freedom is the phase across a Josephson junction or something related to it. And essentially, you can see how these potentials essentially determine very widely different types of energy level structure in these devices. So the transmon has this cosine potential where levels are essentially determined by a nearly harmonic-like potential, so the ladder of levels is nearly equidistant. The fluxonium, so this case here has a double well potential, which leads to very high anharmonicity, so the energy level splittings go from a very small splitting here to much larger splitting farther up, and then you have something similar for the flux qubit. So essentially what is interesting, when you take the simple ingredients that I mentioned in the beginning, so the Josephson, the charging energy, different circuit topologies, you can end up with so many different types of devices. And I think this is something that is probably not yet fully explored in the field. So far people have been looking at devices that are very much based on qubit-like designs, but I would say that in a way, this potential of optimizing these circuits hasn't been fully explored. So now to talk a bit more about what one deals with when building a multi-level system, one first thing to bring up is the fact that when you control these devices, usually you rely on electric driving. So you have some sort of gate where you apply a gate charge Ng, and the operator that matters is this derivative of the Hamiltonian with respect to that particular parameter. And this Hamiltonian, when you look at this matrix element between two energy eigenstates M and N prime, depends on this charge operator N, which then is related to a phase operator. And essentially what is important here is that this comes with particular selection rules, and something that's probably not familiar if you're not in the field is that these selection rules have similarities to what you have in AMO. So if you take the transmon qubit, the selection rules are essentially nearly those of a harmonic oscillator. If you take flux qubits, you have more generally parity-like selection rules, or essentially this energy indices have to have the same parity in order to have coupling between levels. So there are some interesting challenges when it comes to building QuDits, so multi-level system. Namely, these matrix elements typically increase with level index. And this is simply a consequence of the fact that these potentials are essentially eventually dominated by terms that grow at large values of the phase. So this means that essentially as you go up the ladder, the energy relaxation tends to go worse. So that's something that can be a problem if you think of using more and more levels in a superconducting device. There is something similar happening in terms of the phasing. So here with flux noise, usually you can reduce this effect by working on symmetry points as you do with flux qubits. With charge noise, however, even if you have charge noise suppression for lower transitions, as you go up the ladder, this suppression gets reduced. And again, this is something that can come into the picture, as we've also heard earlier today. So I say when you think about some of the advantages of using superconducting devices as QuDits, I think firstly there is this nice flexibility in design which can be put to some use. Again, this I would say hasn't been fully explored. Another very practical but very important advantage when you work on experiments is that you deal with microwave transitions. And here, essentially, you can rely on sources for signals that are all based on relatively conventional electronics. So in a way, it's much easier to scale up the control for superconducting QuDits, I would say, than it is to do so in an AMO system. And finally, I would say coherence times are relatively long as well. So now, when it comes to some of the challenges, as I mentioned earlier, higher levels tend to have decreasing coherence. This advantage of having all transitions in the microwave range also becomes a drawback if you then start to think about possible proximity of these different levels, and in particular this problem increases with the number of QuDits and the number of levels. And one last point to mention as well is that these devices, they never come out to be quite the same. There is variability in the fabrication parameters, so that means that the properties of the QuDits differ, and I would say this is likely a bigger problem than it is for qubits, where it already is a problem in certain implementations. So hopefully this gives a sort of useful picture of what it is interesting and what are some challenges in terms of using superconducting devices for QuDits. So now, leaving this introduction behind, let me move on to the first topic that I wanted to discuss. This is a collaboration with Sahel Ashab, and Sahel has already discussed in some detail the motivation for this experiment. So basically, we looked at the symbol decomposition of a gate for a superconducting qutrit, which can be done in terms of these two generators. So any unitary can be expressed in this form with generators that are diagonal or fully off-diagonal. So this has the advantage that these off-diagonal elements are associated with resonant drives between different levels, and these diagonal elements can simply be absorbed into the gates by changing the phase of the drives that are applied to the different transitions. So as Sahel discussed, there are ways to get to obtain these Hamiltonians numerically, and this this part here describes how you can deal with these diagonal elements. So essentially, if you have a series of these gates, you can attach these diagonal terms to each off-diagonal part by simply incorporating a phase. And this essentially comes down to changing these elements here that are off-diagonal through the addition of a phase factor. So so our device is a flux qubit. It's a superconducting ring with 3 junctions. We developed this design with 3 capacitive shunts, which relative to a more regular flux qubit design has the advantage that it gives a better trade-off between decoherence and harmonicity. When we did this experiment, one important technical advantage we had was that to use a direct synthesis method for the pulses. So this was actually one of the early experiments where this method was used in the field. This technology was relatively new at that time, and we had some experience from older experiments. So where this is very convenient, and in particular think of contrasting this with AMO, is that you can take all of your tones and generate them simply using a digital method. Simply, you basically draw your control waveforms point by point. And this is really spectacular when it comes to how much it simplifies the experiments. It also has some drawbacks, so there are some potential problems in terms of coherence, depending on the experiment that is involved. So we took our system. Spectroscopically, we can identify the main transitions, so 0, 1, and 1 to 2. And we also see for high enough powers, we see a transition in between, which is a 2-photon process that we used in the experiment. So specifically, if we take our qubit, so it has this level structure, and this is approximately to scale in terms of the relative ratios of transition frequencies. When we work at a point that is protected for dephasing, there are selection rules that allow only 0, 1, and 1, 2 transitions. So now to drive 0 to 2, we use a 2-photon process. We did a detailed characterization of this process, looking at the dependence on detuning and on the drive amplitude, and also looking at state tomography. So we see nicely how the population of state 1 is left untouched by this pulse. And we also see how the change of phase in the pulse leads to double the angle in terms of the rotation. One of the most interesting surprises in this experiment was when we started to look at implementing this pulse sequence in relationship to level shift. So we try to essentially look at, well, we have certain matrix elements, we characterize those through 1-photon processes. And we were after implementing a Hadamard gate. So here, starting in in the ground state of the system. By applying the gate, we would expect at the end to have equal population of the state 0, 1, and 2. So what we realized is that if we just turn on the pulses based on the characterization we did for the system, things came out really very much off. So these populations were very far from 1/3. And one thing we realized is that corrections for level shifts are really important. So with superconducting devices, you have the situations where you can actually apply very strong drives, but since the drives couple many levels between them, you actually need to be very careful with stark shifts. And again, this is where this advantage of how you can implement the control comes into the picture. Essentially, what we developed was a protocol where, as we turned on the drives, we essentially compensated dynamically for the level shifts simply by chirping the frequencies that were applied to the system. And this worked really amazingly well. So as soon as we turned this on with proper calibration of the level shifts, we saw how this gate could be, it had this feature that the population came nearly equal. And then we did characterization of the gate using process tomography, and we found the fidelity of 97% once everything was properly calibrated. With this, let me talk about the second experiment we did with this flux-qutrit, which is randomized benchmarking. This is my randomized benchmarking slide, but it's hardly necessary given the fact that this was discussed in quite a bit of detail already. So we deal with the qutrit. The Clifford group has 216 elements. And I remember at the time, so we had a system in the lab, and it was really fortunate that I ran into Barry at some point. He told me about this nice paper they had on the theory of doing randomized benchmarking for a qutrit. So essentially, the experiment applied very, very much the work they had recently done on this topic, the theory work that they had recently done on this topic. So essentially here, we take our same device, this capacitively shunted flux qubit, and we implement a standard randomized benchmarking experiment. I should say there was kind of an interesting twist here. So when we did this experiment, due to logistical reasons, we couldn't implement the pulse sequence that I showed previously, which I assume would have worked a bit better. We instead resorted to the standard decomposition in terms of Givens rotations with 1-photon processes. This still worked pretty well. So this is an illustration of how the populations of the states change with the number of gates. So we see this nice depolarizing channel behavior, or all the populations reach a third at the end of the sequence. The average gate error was somewhere around 1% here. And at around the same time, there were experiments done in Berkeley with the transmon with somewhat better results for the gate fidelity. Using transmon. So essentially, in this experiment, we show that, well, we can reach control of the system at a level that is really quite high. And something that, again, was observed in other experiments is that it's very reassuring to see when you look at the average gate error, it simply comes up to summing up the errors of the individual Givens rotation. So that's kind of a nice result to see in hand. It gives a kind of a nice way to think about how good the control is. One part of this experiment that I want to mention briefly is looking at the behavior of applying repeatedly some of the gates in the Clifford group. So this shows the population of states for repetitions of the Hadamard X, S, and Z gates. And we see this nice repetitive behavior that essentially illustrates the order of these elements in the Clifford group for the different gates. There's also some decay, which is indicative of decoherence. And here, this I should just point this out. This doesn't apparently decay because these are essentially software gates. So they have no decay because it all comes down to corrections in the software. All right, so with this, let me now switch gears and talk about something slightly different. This is theory work we did on the implementation of two-qutrit gates. We've seen a very nice talk earlier today on implementation of gates in superconducting QuDits. So there was quite a bit of work on this topic, and in many of these experiments, the approach taken was to rely on CZ, on say, level shifts in a sense, control level shifts to implement CZ gates between superconducting QuDits. And this was done via microwave activation in Berkeley. And there was also a paper where another approach was used based on a tunable coupler that controls the shift of the levels. So what we were after was the implementation of parametric coupling gates between two qutrits. So, so the motivation for this is the fact that when you look at the coupling, the native coupling between two superconducting qubits, this is transverse coupling. So this is coupling where essentially you have the product of two operators, each of which change the energy state of one of the qutrits. So this is the natural setting for superconducting qubits when you also optimize coherence. So in a way, these are the natural gates to look for in a two-qutrit system. This is what you get simply by capacitive coupling two qutrits to each other. So here, because it's in a way a more transparent and simpler case to look at, we focused on an implementation using transmons. So this diagram here from another paper shows essentially the same setup we used. Two transmons, so these two circuits over here. And another superconducting device in between, which is actually sort of a transmon as well. It just has a very different energy level splitting. This coupler here, this modified transmon, has properties that can be changed when you apply magnetic flux. So essentially, we wanted to use this approach of parametric AC activated gates, where the idea is that these two transmons are off-resonant with each other, but by changing the coupling dynamically using this coupler here, you can essentially establish a resonance condition between these different transitions, and you can implement swap-like gates. And this is an approach that is very well established for the case of qubits, of two-level systems in the field of superconducting devices. This is a diagram from a paper that actually shows the richness of how you can do control in the system, including these swap-like operations. So the first question we ask, well, how useful is this if you can do it? And what we looked at was how you can decompose a qutrit CZ gate in terms of these swap operations. So here we essentially resorted to a numerical search where we were after seeing, well, what is the minimal setting in which you can implement a CZ gate, which we thought is interesting to look at because it's a universal gate. So what we found by trying different combinations is that this gate decomposition here is the most optimal one. So essentially, this decomposition has swap gates between the two qutrits. So these are swaps of type 0, 1 to 1, 0, and 1, 2 to 1, and then finally 0, 1, and 1, 0, with the addition of some single qutrit unitaries. So by optimizing this gate stack here, we found that you can do a CZ gate with only 3 of these operations. These are the numbers that came out, which we don't really have much insight on, but this decomposition seems to be exact. So we looked, after we found this decomposition, we looked at the actual system, taking into account the full energy level spectrum, so taking into account the full complexity of the superconducting circuit, and we carried out detailed numerical modeling for it. So this again shows the two circuits, the two transmons with a tunable coupler in between. This graph here shows the coupling as a function of the applied magnetic flux. So this is the flux applied to this ring. So essentially, the two transmons are off resonant with each other. So if you just let the coupler be, there is no resonant exchange of energy. Now, if you modulate the flux in this loop at the proper frequency corresponding to bringing certain transitions such as 0, 1 to 1, 0 in resonance, then you can induce the swaps that we need. And these two curves over here show the derivative of the coupling strength with respect to flux, which is essentially what says the strength of this coupling. So we did fairly detailed numerical modeling of an actual full protocol. We used the decomposition that I showed previously. So essentially, you have single qutrit gates, and very importantly, the two qutrit gates, the swap-like gates. And as you can see here, so again, these are numerical results. We find that in principle, you can reach very high fidelities with this protocol, with the free two qutrit gates that I mentioned. what I should draw your attention to, though, is that in this model here, we only managed to get this to work with these high fidelities with relatively long pulses. However, we haven't really carried out any detailed optimization of the pulses, which we expect, if we do so, will lead to much shorter gate times. And this is important because this model doesn't include decoherence. Once decoherence comes into the picture, things will get substantially worse. So, just to say a bit more about this two-qutrit gate, one thing we realize is that already the system has, okay, sounds good. One thing we realize is that the system already has many possible collisions between different frequencies that we have to worry about. So we have to make sure to avoid these unwanted resonances by, and we think that we can do much better with the parameter sets that we use. We also think that we haven't really fully optimized this, so there are many aspects that we can look at in more detail. These are qubit and coupler parameters, using pulse shaping to avoid leakage to other states. And also, one other aspect is to see whether we need these swap-like interactions, or we can do even better with more general pulses. We hope that doing this, we can actually get a much better setting in terms of the running time of this gate, which we expect eventually, with good optimization, to be of the order of the coupling strength between the two systems. The last point that I wanted to mention is that there's been some prior work on decomposing unitary operations on two qutrits. Here, our objective was to rely on these two types of entangling rotations, 0, 1, 1 to 1, 0, and 1, 2 to 2, 1. There was some previous work that found how you can use multiple layers of these swap gates to implement arbitrary gates. And our result essentially shows that the CZ gate can be implemented with only 3 of these steps. So that is the best we could find for this particular universal gate. Yeah, so with this, I'd like to summarize. I hope I conveyed that superconducting devices are an interesting platform to do QDIT-based quantum computing and quantum simulations. I talked about our experiments on demonstration of control protocols using simultaneous driving of transitions, and also I discussed randomized benchmarking. And in the last part of the talk, I presented this proposal for an implementation of a two-qutrit gate using AC-activated interactions. With this, thank you for your attention, and I'm happy to take any questions.